All right, so this is Unit 3 Primer Wrap-Up. The question we're answering is, how does the representation for fast constant velocities car motion differ from a slow constant velocity car's motion on? And right now I'm drawing on the position time graph. And most of you drew this, we kind of went over it during class, that the fast constant velocity car is in blue, and then the slow constant velocity car is in gold. And you want to make sure that you're reading the graph correctly. One's a position graph, the other's a velocity graph. And so on a velocity graph, it's just going to be a straight line, right? And the slow moving vehicle is going to be just lower or closer to zero, closer to that time axis, which most of you did draw. Okay, and then you want to remember, for constant velocity, there's only one speed. So if it's fast, it's still going to be just one slope. All right, so then that's one slope, and then on the velocity graph, it's just one velocity, right? So that one slope means that there's only one velocity. And so even though we have two different lines, that line is never changing. And so on the velocity graph, it looks like it's also just one thing that never changes. So that's what a constant velocity is going to look like on a position and a velocity graph. All right, so now let's go ahead and draw it for our motion map. So the fast constant velocity, I think what I remember, right? You told me that the dots were kind of further spaced apart and that the arrows are going to be longer. And we want to draw our arrows closer to the next dot as close as possible. And don't forget to label your time as equal to 0. And so same thing for slow, it's not going to be as widely spaced apart, right? So it's going to be closer together. The arrows are shorter. It looks like it's covering less distance than the fast moving vehicle. All right. And now for our computational representation. This is just basically our pirate code, our next x. So next x, and then it's going to have two inputs, the two argument function. So it's going to be number, comma number, and our output is going to be a number. Okay, it's going to give us our next x number. So for our examples, we just have next x. Let's pick -4 and 2. All right, and so let's see. All right, so next x, -4, 2 is, and let's go ahead and write is, and then we're going to write the way it should be calculated, right? And so it's just -4 plus 2 times our delta t. And remember, in Pirate, it doesn't know to read x as the multiplication sign, so we use the asterisk. Next x, and then another 2 argument, 4.2, comma 5.3 is 4.2 plus 5.3. And so this is just our standard function definition, or our standard function. And we're going to go ahead and write the function definition down here. Next x, and then x for position, v for velocity is going to be x plus, and then don't forget your parentheses, v times delta t. Okay, definitely forgot the parentheses, so make sure you don't forget the parentheses, okay? And so I'm going to go ahead and erase this velocity here so that we can change it to be some other number, right? So 15.3, that sounds like a pretty big number, 15.3, and I'm making up these numbers, right? And so for the slow moving vehicle, we can do 2. Okay, and so we have -4 plus 2 times delta t. And so our slow constant velocity motion is going to have a lower velocity, and our fast constant velocity is going to have a higher velocity. All right. Okay, now for the verbal representation, a fast constant velocity car. So it's a car. So a fast car has a bigger, no, let's not use covers more. Fast car has a bigger change in position than a slow car for the same change in time. And so for the same amount of time, the fast car is going to have a bigger change than the slow car. All right, and so we'll see that it covers more distance on our motion map and on our position graph. All right, and our mathematical representation is just that the final position is equal to the initial position plus v times delta t. Okay. All right, and so for the next page, we have that what does it mean for the dots that are wider spaced? What does it mean for the velocity arrows to be longer? And so the wider spaced dots means that the larger change in position represents a fast moving object, right? So here in our motion map, we can see that the blue one is showing that the dots are further apart, the arrows are longer, and so in comparison to the gold color car or the slow one, there's less change, right? So wider spaced dots mean a larger change in position, and it represents a fast moving object. So the longer arrows show a fast moving object. All right, and then the next question, on the position time graph, describe the slope of the fast car in comparison to the slower car. A fast car slope is steeper, slower car slope is less steep or flatter. And that's something that you all remembered from last semester. All right, on number 3, on the velocity time graph, how do the graphs and values differ between the fast and slow car? So a fast car will be farther away from 0. And so on the velocity graph, it's just going to be higher up or just further away from 0. And then the slower car is going to be closer to the time axis. Okay, and so let's go ahead and draw that out. So let's go ahead and draw the velocity axis and then the time axis here. And we'll draw the fast car first. So the fast car will be either positive or negative direction. It's going to be far away from the time axis. The slow car will be closer to the time axis, like so. All right, so then again, the blue lines represent the fast car, and then the gold ones right here represents the slow car. All right, question number 4. What does delta x change in our picture? So delta x just means our change in position. So that means in our picture, our car is going to be further apart. So the change in position is going to be further apart if it's fast, or if it's a small number, it's going to be closer together. All right, number 5, how would a position time graph and a velocity time graph look for an object that starts slowly and gradually gets faster? So let's go ahead and draw some slopes that are different. And so slow car has like a flatter slope. So I'll try to draw one that's flat, and I'll just try to change it up for each of the times. Right, and so you can see that my slope is getting larger each time. It's getting steeper. And so now I'm not going to draw it for the velocity time graph, but what do you think that's going to look like on a velocity time graph? If my slope is changing on the position graph for each second, what's that going to look like on the velocity graph? So you can see, I'm just going to break it up into seconds here, that the slope is changing. How? Probably slope is getting steeper because it's getting faster. So there's a changing slope, which means that the velocity is no longer going to be some sort of flat line, right? So go ahead and fill that part out.